In the cold, silent vastness of the cosmos, light usually means life, or at least predictability. But 13 billion light-years away, there's a galaxy whose light shouldn't exist. According to everything we know about physics, star formation, and the very birth of galaxies, simply too bright, too early, too powerful. It's like finding a roaring bonfire in a place where fire hasn't been invented. Scientists call it GUNZ11. But this isn't just a technical anomaly. This could be a crack in the foundation of cosmology itself. Because if this galaxy exists, then maybe everything we know about the beginning DOESN. Single quotes to subscribe if you believe the universe still holds secrets we're not ready to understand. Join us as we unravel the mystery of a galaxy that defies the laws of cosmic time itself. It began as a whisper of light, barely a ripple in the fabric of space-time, stretched thin across more than 13 billion years. When the Hubble Space Telescope first captured it in 2016, no alarms went off, no grand revelations, just a point of light on a distant image, a smudge that didn't quite belong. It was only after the data was run, rerun, and peer-reviewed that something astonishing emerged. This wasn't just any galaxy. This was the galaxy, GUNZ11, and it was older than anything we'd ever seen. GUNZ11's light came from a time just 400 million years after the Big Bang. To grasp how early that is, imagine the entire history of the universe compressed into a single calendar year. The Big Bang would occur at midnight on January 1st. The Earth forms in early September. Dinosaurs roam in late December. Humans arrive minutes before midnight on New Year's Eve. GUNZ11's light. It comes from January 4th. That's how close to the beginning it is. But this isn't just about being old. What stopped scientists in their tracks wasn't its age. It was its brightness. By every model we've built, the early universe was dark, chaotic, and slow to form structure. Galaxies should have been faint whispers, small pockets of gas and dust slowly collapsing under gravity. But GUNZ11, it blazed like a cosmic lighthouse, 10 times brighter than anything that should exist at that time. It was, quite literally, impossible. And suddenly, every cosmologist had to ask themselves, what did we miss? The discovery shook the foundations of what we thought we knew. Dr. Pascal Oster, the lead author of the study, described the moment with a kind of stunned reverence. We weren't looking for the most distant galaxy. We were just analyzing deep field data. And there it was like finding a fossil that predates the Earth itself. The light had traveled 13.4 billion years to get here. That means when that light first left GUNZ11, the Earth didn't exist. The Sun didn't exist. Even the Milky Way was still forming. And yet here it was, captured by human eyes and silicon sensors orbiting Earth. Just think about that. That light existed long before we did, and it waited all this time to be seen. The redshift of GNZ11 was measured at 11.09 A, number so high it staggered cosmologists. Redshift is how we measure cosmic distance. As the universe expands, light stretches, like a rubber band pulled tight. The higher the redshift, the further back in time we're looking. GUNZ11 shattered the previous record by nearly 200 million years. That may not sound like much, but in cosmic terms it's enormous. Like finding a library in a world that hasn't discovered fire, and yet this light defied more than just chronology. It defied physics. By our understanding, Galaxies need time for gravity to pull gas into clumps, time for stars to form and ignite. Yet Jianzi-11 was already a fully fledged system, bursting with newborn stars and radiating far more energy than its age should allow. The laws of physics said this galaxy shouldn't be possible. But there it was, so the questions began. Was this an error in the data? A misinterpretation of the redshift? Teams across the globe double-checked the numbers. The measurements held. Jianzi-11 was real, and its existence was screaming at us. Your understanding is incomplete. It wasn't long before headlines started spinning. Oldest galaxy ever found. Rewriting the universe. The light that shouldn't exist. But behind the bold text and artistic impressions was a deeper emotion, one most articles didn't show. Fear. Because if Jianzi-11 could exist when it shouldn't, then our models of the early universe, of star formation, of cosmic evolution, might all be flawed. What else might be out there, hiding in the early dark, waiting to remind us that we're not nearly as smart as we think? This isn't the first time light has challenged our assumptions. In 1929, Edwin Hubble discovered that galaxies were moving away from us, proving the universe was expanding. That revelation transformed cosmology overnight. And now, nearly a century later, another flash of light, this one older, quieter, deeper, might be whispering another cosmic truth. But we're not just passive observers, we're interpreters, decoders, dreamers. Imagine this: you're an astronomer, staring at a point of light so old, it predates your concept of time itself. What do you feel? Disbelief? Joy? Existential dread? Drop your thoughts in the comments, because this moment isn't just about the universe, it's about how we respond. When the universe pushes back, GN-Z11 isn't just a record breaker. It's a warning flare, a signal from the past, reminding us that we're still students of the stars and that sometimes the cosmos refuses to follow our rules. But this was only the beginning. The real shock was still to come, because when scientists tried to understand why Jianzi-11 burned so brightly, the answers only deepened the mystery. What would you do if you looked into the past and it looked back? In the earliest days of the universe, there were no stars, no galaxies, just a vast, seething fog of hydrogen and helium, formless, silent, and dark. This era is known as the Cosmic Dark Ages, a time before the first points of light pierced the void. By all models, this phase should have lasted hundreds of millions of years, and yet Jianzi-11 was already glowing, and not just glowing, blazing. From its staggering redshift and spectral data, astronomers were able to estimate something truly perplexing. Jianzi-11 wasn't just an early bloomer, it was forming stars at a rate over 10 times faster than expected for its age. Its mass, already close to 1 billion times that of our Sun, was completely out of line with the young universe. It was as if you found a fully grown adult walking out of a maternity ward. This was the riddle that haunted Dr. Pascal Osh and his team at Yale University. These were seasoned cosmologists, veterans in interpreting the faint whispers of early galaxies. But Jianzi-11 wasn't whispering, it was screaming. Dr. Osh recalls reviewing the photometry, expecting the redshift value to drop after recalibration. Instead, it held steady. It felt like nature was lying to us, he said, like the cosmos had skipped a step. But nature doesn't lie. It just waits for us to ask better questions. So they turned to simulations, vast digital replicas of the early universe, built from millions of lines of code, math, and theory. They loaded the parameters: an infant cosmos, sparse matter, limited metallicity, low gravitational clumping. Then they told the computer, show us what galaxies should look like 400 million years post-Big Bang. Over and over again, the results came back the same: faint, fragmented, weak, but never like this, never. Like GN-Z11, the galaxies simply would not form inside their models. Not at that brightness, not at that density, not with that speed of star formation. It was like programming a forest to grow and watching a skyscraper erupt instead. This triggered a chain reaction of questioning. Could the physics behind dark matter be off? Could some unknown mechanism be accelerating gas collapse in pockets of the universe we've yet to understand? Some theorists propose that dark matter may have clumped together much faster in the early universe, forming deep gravitational wells where stars could ignite quickly. Others floated the possibility of primordial black holes seeding early. Galaxies' massive ancient voids pulling in matter fast enough to form these stellar bursts. But these were just guesses, and worse, none of them explained the sheer luminosity of GN-Z11. Its ultraviolet output indicated a staggering population of hot young stars, tightly packed, burning through their short lives like cosmic supernovas in waiting. The starburst activity was 20 times higher than what's typically expected from galaxies even twice its age, which raised another problem. Where did all the material come from? In the early universe, the interstellar medium was barely enriched. There hadn't been enough time for generations of stars to create heavier elements, the very ones necessary for efficient star formation. It would be like trying to build a city with no bricks, no roads, no machines, just dirt and gravity. And yet GN-Z11 was a metropolis in full swing. Somewhere in the shadows of these equations, something wasn't adding up. Dr. Osh wasn't alone in his doubts. Teams at Caltech, the European Southern Observatory, and Japan's Subaru telescope started re-examining their own deep field datasets. Were there other GN-Z11s hiding in the static? Were these rare anomalies, or symptoms of a much deeper blind spot? And maybe the most haunting question of all, what if this isn't the outlier? What if this is the rule and we've just never looked deep enough to see it? Because that would mean our entire model of cosmic evolution, from how galaxies form, to when they shine, to what the early universe even looks like, would need rewriting, not tweaking. Rewriting. Imagine spending decades building a jigsaw puzzle only to discover the edge pieces don't fit. That's the emotional terrain many cosmologists found themselves navigating, a mix of awe, confusion, and scientific dread. As one anonymous researcher admitted during a private cosmology workshop, it's like the sky is trying to tell us something we're not ready to hear. So, what is it trying to say? Maybe GN-Z11 isn't just a galaxy. Maybe it's a question. Mark burned into the early sky a message, not in words, but in photons. A flare that says, look again at your assumptions, at your timelines, at your models, because something in the darkness is illuminating more than just space, and the scariest part, GN-Z11 might not even be the strangest thing. We'll find in the next chapter. We'll look at a property of this galaxy that makes the mystery even more tangled: its light. Not just what it reveals, but how it behaves. Because the deeper scientists dug, the more they realized something unsettling. GN-Z11's light might not just be bright. It might be breaking the cosmic speed limit. Light travels at 299,792 kilometers per second, unwavering constant etched into the laws of physics. Nothing in the known universe outruns it, and over vast cosmic distances, this light stretches, shifts, and dims. It carries with it not just illumination, but history, time, proof of where and when something existed. It's how we peer across the gulf of space and say, with confidence, this is how the universe used to be. But what if that light, the light from GNZ11 reached us, bathed in redshift? Specifically, a redshift of 11.09, an almost incomprehensible number. The redshift scale, for most astronomers, is like a clock, a cosmic ruler. The higher the number, the further back in time we're looking. Most well-known galaxies sit comfortably between redshifts of 0 and 3. Even the previous record holder barely touched redshift 8. GNZ11 smashed past them all. At redshift 11.09, we are no longer just looking into the past. We're looking into the primordial, into an epoch when the first atoms were barely cooling, when cosmic microwave background radiation still hummed around every corner of space. This wasn't supposed to be a place for structured light, and yet the photons that arrived from GNZ11 weren't just coherent, they were stubbornly organized. They formed a spectrum, a shape, a fingerprint. That fingerprint told scientists, this is a galaxy. And I was burning bright when I shouldn't have even been born. But how could that light be so strong after 13.4 billion years of cosmic travel? Here's the paradox. As light journeys through space, it stretches with the universe's expansion. That stretching reduces its energy and shifts it toward the redder, cooler end of the spectrum. This is the very foundation of redshift theory. Yet the spectral data from GNZ11 showed far more clarity than expected, a coherence and intensity that shouldn't have survived that journey. Imagine shouting from across a canyon for 13 billion years, and still being heard in full voice. It didn't make sense, and worse, it suggested something else might be wrong. Some physicists quietly began to ask, are we measuring distance correctly? Redshift isn't just a light trick, it's a statement about how fast the universe is expanding. And that expansion has been calculated using the standard CDM model, the cornerstone of modern cosmology. But here's the twist. GNZ11 forced scientists to reconsider whether our yardstick itself was flawed. Was the universe expanding more quickly in its infancy than we believed? Or did GNZ11 simply exist closer than the redshift implies? Neither answer is comforting. In one scenario, the early universe had sudden, unexplained bursts of rapid inflation that defy current models. In the other, light from GNZ11 may have been affected by exotic phenomena we haven't even theorized. Yet gravitational lensing by ancient dark matter halos, early universe time dilation, or even, as one controversial paper suggested, a kind of light echo from a collapsed dimension. And then there's the speed limit. If GNZ11's light arrived too early based on its calculated distance, are we saying the light traveled faster than it should have? Not exactly. But it would mean our understanding of cosmic velocity, how fast space can itself stretch, may be underestimating something. And that's where the idea of super expansion creeps in. According to general relativity, space itself can expand faster than the speed of light. During inflation, this supposedly happened. But that was in the first split second after the Big Bang. What if GNZ11 is evidence that such inflationary pulses happened again, later, in pockets we never expected? That's what began keeping theorists up at night, We spoke with Dr. Rajan Chaudhary, a cosmologist based at the Inter-University Center for Astronomy in Pune, India. He's been studying exotic inflation models for over a decade. If this galaxy is where we think it is, he says, then the universe is playing tricks with scale. Space might not be expanding like we thought, not smoothly, but in surges. That could mean there are places, times, even objects that are older than the expansion should allow. Suddenly, GNZ11 isn't just a galaxy. It's a time capsule from a version of the universe we haven't yet mapped. But there's a deeper implication, one that shifts the conversation from physics to philosophy. If light can arrive too strong, too soon, how much trust can we place in what we see? Could other observations of distant quasars, dark matter halos, or gravitational waves so be warped by unknown variables? Are we building our understanding of the cosmos on a ruler that keeps changing size? And what about the light that hasn't reached us yet? Could there be entire epochs of galaxies waiting, hidden just beyond our reach, not because they're too far, but because we're asking the wrong questions? GNZ11 may be the first in a series of cosmic breadcrumbs, clues that the story of the universe isn't just longer than we thought, but stranger. And if its light really is a glitch in the cosmic expansion model, then we may be standing on the edge of a scientific revolution. But before we rewrite the universe's rules, we must ask a more unsettling question. What if this galaxy isn't from this universe at all? What if GNZ11 didn't just break the rules of this universe, because it doesn't belong to this universe at all? In the soft hum of physics symposiums and the quieter corners of theoretical departments, there's a whisper that dares to become a roar, the multiverse. Once a fringe concept reserved for science fiction and late-night philosophy debates, the idea of multiple universes is beginning to sink its teeth into real equations. And in the wake of GNZ11's impossible light, its age, brightness, coherence, some physicists are daring to wonder. What if we're not looking into our past, but into somewhere else entirely? The theory isn't as wild as it seems. According to inflationary cosmology, the universe didn't just expand after the Big Bang, it exploded into existence, expanding faster than light in a process called cosmic inflation. But here's the kicker. Some versions of this model suggest inflation didn't stop everywhere at once. Instead, it ended in patches, bubbles, each becoming its own universe. Ours is just one bubble, and next to us, countless others. Some call it the multiverse, others call it eternal inflation. But either way, the implication is staggering. The observable universe we see is just a sliver of something far vaster, a cosmic archipelago of disconnected realities, each with its own rules, constants, and history. And that's where GNZ11 becomes more than a galaxy. It becomes a candidate for what physicists refer to as a cosmic bleed-through phenomenon, where gravitational, quantum, or even energetic remnants from one universe leak, echo, or shimmer into another. Think of it like two soap bubbles touching. For a brief moment, their membranes overlap. That edge could be what we're seeing in GN-C11. One of the boldest voices in this field is Dr. Laura Seinhoughton, a theoretical physicist who's spent years arguing that quantum entanglement across cosmic boundaries might leave imprints in our universe, strange anomalies we can't explain through local physics alone. When shown the light signature and redshift properties of GNZ11, her reaction was chilling. This could be exactly the kind of signal we've predicted. Not a glitch, not an error, but a reflection of a neighboring universe. a mirror to a physics we haven't discovered. Let's break this down. If another universe formed with slightly different parameters, maybe faster early structure, formation, a different balance of dark energy, or even altered dimensions, then galaxies like GNZ11 could be normal there. But viewed through the warped lens of our own space-time, they would appear distorted, bright when they should be dim, ancient when they should be impossible. So the question isn't just what is GNZ11, it's where is it from? Imagine a lighthouse, appearing on the horizon of an ocean you believed had no shores. You scramble to identify its architecture, its light source, its fuel. But all your calculations fail because it's not built from your world. It's not even sitting on your sea. It's beaming from another coast entirely. Could we really be seeing across universes? One possibility involves quantum tunneling, bizarre but real phenomenon where particles can appear in places they shouldn't, bypassing classical energy barriers. Some physicists have proposed that on the largest scales, whole quantum states of energy could tunnel between dimensions or adjacent universes. If GNZ11 sits near one of these inter-universal thin spots, it could be partially visible to us, like seeing a candle flickering through a fogged window. Another candidate is gravitational lensing, where massive structures bend and magnify light from behind them. But GNZ11 isn't being magnified. It's being misunderstood. If its light took a shortcut through a higher dimensional fold, what some call a brain breach, then it may have traveled not across space, but through a shortcut we haven't learnt to measure yet. And if that's true, then it gets weirder. We may have already seen other cosmic anomalies, unexplained cold spots in the cosmic microwave background, odd alignments in galaxy spins, or strange statistical anomalies in large-scale structure surveys that are signposts, leftovers from universe-to-universe contact. So why don't more scientists scream this from the rooftops? Because it challenges everything. The scientific method is built on falsifiability. If we can't test the multiverse, how do we study it? How do we prove that GNZ11 came from a different realm of physics? These are questions that push the very boundaries of what science can do, and yet, here we are, with a galaxy that shouldn't be, with light that doesn't add up, and a growing suspicion that maybe, just maybe, we're seeing farther than our universe allows. Now, ask yourself this: if another universe were visible for only a sliver of cosmic time, would we even know what we were looking at? Or would we dismiss it as an error, a data glitch, a puzzle we're not yet equipped to solve? GNZ11 might be our first brush with that mystery, a ghost not of the past, but of a parallel present. And if it is from a neighboring universe, that raises a chilling thought: are we the observers, or are we the ones being seen? In the next chapter, we leave theory behind, dive into the cold, hard logic of machines. Because when humans couldn't explain GNZ11, they turned to artificial intelligence, simulations, algorithms. But what happens when even the machines can't recreate the impossible? When the laws of nature fail to explain the universe, we turn to machines, not for answers that first, but for guidance, for structure. Simulations are the modern telescopes of the mind, letting us build virtual universes and fast forward through billions of years in seconds. They allow us to ask, if we run the universe again, will GNZ11 appear? And in late 2016, after the galaxy's discovery had rippled across the astrophysics community, that's exactly what scientists tried to find out. They turned to the most powerful, tools at their disposal, cosmological simulations like Illustris, Eagle, and Millennium codebases built by international collaborations, spanning petabytes of data, running on supercomputers that cost tens of millions of dollars. These weren't just random models. These were the best representations of the universe we'd ever constructed, complete with dark matter, halos, baryonic gas flows, and star formation recipes refined over decades. Into these simulations, researchers plugged the conditions of the early universe, 400 million years after the Big Bang: low metallicity, sparse matter, cool cosmic background. Then they ran the numbers again and again, and what did they find? Nothing, or rather nothing like GN-Z11. No matter how many times they tweaked the parameters, increased resolution, or changed seed values, nothing came close to forming a galaxy with that mass, that brightness, that level of organized complexity. It was as if the simulation refused to give birth to GN-Z11 over thousands of runs. It never once appeared. Imagine asking a machine to recreate Beethoven's Fifth Symphony, and it only ever outputs static. Dr. Claudia Vergara, a lead researcher on the Renaissance Simulation Project, described her frustration. We can create analogues of the Milky Way, of Andromeda, even of ancient galaxies with high redshift. But GN-Z11, it's like asking a child to recite Shakespeare before learning the alphabet. Some tried brute force, feeding the AI terabytes of observational data, increasing simulation resolution to subgalactic scales, letting machine learning algorithms adjust parameters autonomously. The result, more elegant early universe structures, but still no GN-Z11. No answer to why it was so bright, so fast, so soon, which raised a haunting question. Are our models blind to something fundamental? Simulations are only as good as the physics we program into them. They don't discover, they mirror our assumptions. If we've misjudged early star formation, misunderstood the behavior of dark matter, or omitted unknown forces entirely, then our simulations can never give us the truth, only the echo of our ignorance. And here lies the philosophical twist. The more simulations failed, the more a dangerous idea resurfaced, one that had been waiting in the shadows of academic forums and speculative panels. The simulation hypothesis, the theory popularized by philosophers like Nick Bostrom and whispered about in tech circles, posits that our universe might itself be a simulation, a computational construct running inside a vastly more advanced intelligence, not metaphorically, literally. In such a framework, anomalies like GN-Z11 aren't just curiosities, they're glitches, rendering errors, procedural oversights, the kind of artifacts a program might produce if it's trying to simulate a vast cosmos with limited precision. Of course, that's a heavy claim. Most physicists dismiss it. But the failure of our best simulations to produce GN-Z11 lent the idea a strange credibility. Not because it proved the theory, but because it exposed our dependence on models, our faith in them, faith that the universe follows rules we can encode. But what if GN-Z11 is the universe's way of breaking that faith? Let's rewind. Why do we even trust simulations? Because they've worked mostly. They've predicted galaxy clustering, star population, evolution, cosmic microwave background patterns. But these are outcomes based on our current physics, and GN-Z11 steps outside that boundary. It challenges the very inputs we feed our digital oracles. It's like giving a map to a city and then stumbling into a neighborhood that isn't on it, a place that shouldn't be built, a place that violates zoning, architecture, and logic, but it's there, with people living in it, lights glowing in the windows. What do you do with a discovery like that? Do you assume your map is wrong? Or that the city is changing in ways your map can't capture? Or do you wonder if someone else is drawing the map as you walk? Some researchers took the opposite approach. Instead of trying to make GNZ11 fit the simulations, they asked, what kind of physics would naturally produce it? That meant changing the rules, boosting early dark matter densities, introducing unknown bosonic fields, adding variables no one had dared touch before. And guess what? Even then GNZ11 remained elusive. This wasn't just about tweaking knobs. This was about rewriting the blueprint. By the end of 2019, GNZ11 had become a sort of digital phantom. Every time a team thought they'd cornered it, the simulation broke. Or worse, it worked, but produced dozens of similar galaxies, none of which matched what we actually see in deep field observations. So maybe the failure wasn't in the simulations, but in the assumption that reality can be simulated at all. We've reached the point where our machines can model black holes colliding, neutron stars spinning, entire clusters dancing through gravity. But one little galaxy, barely the size of a pixel in the night sky, has outwitted them all. And if that's true, if GNZ11 is beyond what our best simulations can reproduce, then maybe we're not observing a glitch in the simulation. Maybe the simulation is ours and GNZ11 is real. Next, we venture into the very heart of this mystery, inside the galaxy itself, a furnace of impossible star birth. Because if simulations can't explain how it formed, maybe it's time to witness what it's doing. At the core of GNZ11 lies a contradiction so profound, it almost feels mythological. A galaxy that should be struggling to form stars is instead churning them out like a furnace gone mad. This isn't poetic exaggeration, it's astrophysical fact. GNZ11 is producing new stars at a rate nearly 20 times greater than our own Milky Way, despite existing at a time when the cosmos was barely 3% of its current age. For context, that's like a toddler lifting a truck. It's not just improbable. It's a violation of scale, of energy, of everything we thought galaxies could do that early in the universe. But GNZ11 is doing it. Star formation requires a delicate balance. First, gas must cool and collapse under gravity. Then, turbulence and magnetic fields shape that gas into dense regions called protostellar cores. Over time, nuclear fusion ignites, birthing a star. But in the early universe, gas was hot, was low, and thus the scaffolding for star birth was rare. In that environment, forming even a few stars was difficult. Forming hundreds per year. That's absurd, and yet, GNZ11 shines with ultraviolet brilliance, the unmistakable fingerprint of massive, short-lived stars forming in rapid succession. These aren't small, quiet stars like our sun. These are blue giants burning fast, dying young and flooding space with light. So how is this happening? Dr. Rebecca Larson, an astrophysicist working with data from the James Webb Space Telescope, describes GNZ11's stellar birth rate as an engine running without fuel. She explains, it's as if this galaxy had access to some hidden store of enriched material, heavy elements, cool gas, maybe even dust that shouldn't have existed yet. By all accounts, it's building stars faster than nature allows. 1. possibility is that GNZ11 experienced a hyper-efficient collapsar period in which vast amounts of primordial gas collapsed almost instantly, triggered by exotic conditions we don't yet understand. But even that would only explain part of the puzzle. The more troubling question is, where did the raw material come from? Heavier elements carbon, oxygen, iron are formed in the hearts of stars and spread through the universe by supernova. That process takes time, generations. GNZ11 didn't have that time. And yet, its light suggests the presence of these elements enough to support aggressive star formation and potentially even early planetary systems, which raises a chilling possibility. Are we wrong about the timeline of stellar evolution itself? Some theorists now wonder whether the first stars, what we call population 3 stars, may have lived and died far faster than expected, seeding galaxies like GNZ11 with the materials needed for explosive growth. These theoretical stars would be massive, hundreds of times the mass of our Sun, and burn out in just a few million years. They would go supernova quickly, enriching their surroundings with just enough metal to spark a new generation of stars. And fast. But here's the problem. We've never seen a population 3 star. Not directly. They remain hypothetical, ghosts expected, but never confirmed. And so GNZ11 forces us to confront a grim reality. We might be looking at effects with no confirmed cause. Some scientists speculate about early supermassive black holes acting as catalyst, disturbing gas flows, compressing star-forming regions. Others point to exotic dark matter interactions or quantum instabilities in the fabric of early space. But none of these ideas are more than whispers. No model, no equation, no simulation has definitively answered how GNZ11 became a cosmic factory. At a time when the universe was still fumbling through its infancy, and there's something else, a subtle but profound implication hiding in the numbers. If GNZ11 can produce stars this rapidly, so could others. It might not be a unique case. It might be the first of many, a vanguard of hidden galaxies, lurking just beyond the reach of our instruments, rewriting our assumptions about when and how the first light of the universe truly dawned. Which leads to a haunting reflection. What if the early universe wasn't dark and quiet at all? What if it was a roaring storm of creation, and we just weren't listening with the right instruments? James Webb is already beginning to hint at that possibility. In just its first few deep field surveys, it's begun to uncover galaxies with similar traits: compact, hyperluminous, ancient beyond belief. The darkness we once assumed may have been filled with fire. Still, GNZ11 remains the brightest flare. A cosmic anomaly that insists on attention. A machine of stars, operating at maximum output at a time, when even its parts should not have existed. And maybe that's the key. Maybe GNZ11 isn't just a mystery. Maybe it's a message, a signal encoded in the fabric of light, daring us to rethink the rules of cosmic genesis, to acknowledge that the universe didn't tiptoe into existence. It may have exploded into complexity far sooner than we imagined. And if stars could burn that hot, that early, what else could have formed beside them? That's where we go next. Because GNZ11 may not be alone in the next chapter. We step beyond this one galaxy into a growing catalogue of ancient light, ghostly galaxies emerging from the dark. If GNZ11 is a clue, how many others have we simply missed? For years, GNZ11 stood alone, like a torch in the primordial night, singular, isolated, inexplicable. But what if it wasn't alone? In 2022, as the James Webb Space Telescope opened its golden hexagonal eyes to the deep sky, the darkness began to crack. Within weeks, it revealed something extraordinary. G11 was just the beginning. All across the field of views, scattered like ancient embers, were other galaxies, faint, redshifted, and impossibly old. Galaxies that shouldn't exist, not yet. Some even brighter, some even closer to the Big Bang. Astronomers were stunned. The data streamed in like a revelation. Galaxies forming within 300 to 400 million years after the Big Bang. Their numbers didn't just challenge the standard model, they threatened to rewrite it. Until then, G11 had been viewed as an outlier, a statistical fluke, a single point on an otherwise clean graph of galactic evolution. But now, the graph was breaking. The points were multiplying. Something was off, and perhaps it had always been. Many of these galaxies had gone unnoticed by previous telescopes, buried in noise or mistaken for more recent objects. Hubble could glimpse them, but not resolve them, like silhouettes behind frosted glass. But Webb could see clearly, and what it saw was a crowded early universe. We had imagined the first billion years as quiet, sparse, a dark canvas, slowly painted by scattered starlight. But what if that canvas was already crowded with brushstrokes? Enter CEERS 93316. Another galaxy that came to light shortly after G11's reign was challenged. Estimated to have formed just 250 million years after the Big Bang. It may be even older than G11, and it's not alone. Dozens of candidates have followed each, whispering the same message. We were here all along. These are the ghost galaxies of the early universe, hidden not by distance, but by expectation, because for decades we weren't even looking for them. The CDM model, which governs our understanding of cosmology, told us not to bother. Star formation was supposed to be inefficient. Galaxies, sparse, dull, dim, but these galaxies defied that. They were bright, compact, organized, and they were everywhere. It's as if we'd been watching a silent film, only to realize we had the sound turned off. Dr. Emma Curtis-Lake, a principal investigator on Webb's Deep Field Imaging team, described, "At best, we thought the early universe was asleep. But these galaxies tell us it was wide awake, busy, vibrant, forming stars at breakneck speed. So now we ask, how many more have we missed? And if our instruments were blind until now, how long has the early universe been trying to tell us its true story?" Some cosmologists now believe the galaxy formation timeline may have to shift dramatically by hundreds of millions of years. That's not a small adjustment. That's like rewriting the first chapters of a novel you thought you'd already read. But the implications run deeper than chronology. If galaxies were forming early and rapidly, it changes the entire chemical history of the cosmos. Heavier elements would have been forged sooner. Supernova would have peppered space with building blocks earlier. The first black holes could have formed before our models even predict their seed stars were born. In other words, these ghost galaxies may have rewritten the ingredients list of the universe, and yet, the most haunting part is how invisible they were until now. It makes you wonder, what else are we not seeing? Could there be even older galaxies, just beyond Webb's range? They're objects forming in shadows we haven't learnt to illuminate, or entire populations of cosmic structures so unfamiliar, so outside our predictions, that we mistake them for background noise. Drop a comment. What do you think is still hiding out there? And while we imagine the invisible, here's a thought. What if some of these galaxies vanished not just from view, but from existence? Some astrophysicists suggest that extreme gravitational environments in the early universe, like those surrounding primordial black holes, could have torn some galaxies apart shortly after they formed. Others may have merged into larger structures before their light ever reached us. What we're seeing now may be just the lucky few survivors. The ghosts of a cosmic battlefield we're only beginning to uncover. And then there's a more unsettling idea. What if some galaxies in the early universe evolved so fast they burned out before our telescopes ever turned toward them? In this view, GNZ11 and its cousins aren't just ancient, they're posthumous. Dead galaxies whose light only now reaches us. Their stars long gone, their structures collapsed or consumed, and yet their light lives on, like a voice echoing from an empty room. That's the power of these ghost galaxies. They force us to confront the fragility of cosmic history, how easily it could slip past us, how much we've missed not just because we couldn't see, but because we never imagined it was there to begin with. And if these galaxies are real, and they are, then the foundation of our cosmology is wobbling, because the story of the universe's first billion years is no longer about a slow dawn. It's about a brilliant, chaotic morning we slept through. Next, we'll return to that wobbling foundation, to the very physics we've trusted for decades. Because if GNZ11 and its ghostly siblings are real, then something in the physics itself might be missing. Maybe, just maybe, the universe is using these galaxies to tell us we've been wrong all along. There comes a moment in every scientific revolution when the facts become too heavy to ignore. The observations pile up, the equations begin to fray. The stories we tell ourselves about how the universe works, about what can and cannot exist, start to sound like rumors from another age. GNZ11 and the ghost galaxies joining its spectral parade have brought us to such a moment. The evidence is too bright, the implications too stark. Something in our physics is missing. For decades, cosmology has relied on a foundation called the CDM model, lambda cold dark matter. It's a mathematical tapestry that threads together the expansion of the universe, the nature of dark matter, the mysterious push of dark energy, and the growth of galaxies from cosmic seed to starlit city. It's worked beautifully, until now, because these galaxies should not exist, not this early, not this bright, not this organized. So what's wrong? First, there's the problem of timing. Our models say it should take hundreds of millions of years for gas to collapse into the first stars, and even longer to assemble into coherent galaxies. Yet here is GNZ11, already a billion solar masses strong, shining just 400 million years after the Big Bang. Here are its kin, forming at similar or even earlier times. Then there's the problem of quantity. The number of early galaxies we're seeing isn't just a little higher than predictions, it's orders of magnitude higher. That isn't a rounding error, that's a chasm. Some theorists have begun to wonder, are we missing a fundamental piece of cosmic physics? Is there an unknown ingredient at work, a force, a particle, a field that makes early star and galaxy formation easier, faster, more efficient than we ever imagined? One possibility is the existence of early dark energy, a brief, powerful force that accelerated the collapse of matter in the young universe before fading away. If true, this could have given star-forming regions a gravitational boost, compressing them into blazing life far ahead of schedule. But early dark energy is, at this point, more ghost than substance. The search for its signature is ongoing, another avenue. Exotic particles, known cousins to the familiar protons, electrons, and neutrons could have shaped the early cosmos. Some theorists propose pre-quantum fields, a kind of cosmic scaffolding that allowed matter to clump together with shocking speed. Others look to the frontier of string theory and higher dimensions, where new physics might operate outside our perceptual reach. And then there's the possibility that our most basic constants, like the gravitational constant or the speed of light, weren't so constant after all in the universe's earliest days. If even one of these shifted, even slightly, in the primordial fire, the entire timeline of cosmic evolution could change. It's a provocative idea, but also a dangerous one. It calls into question the very fabric of everything we measure. Scientists like Dr. Samuel Dorelli, a theoretical physicist at the Institute for Advanced Study, are open about the implications. Every time we encounter a result like GNZ11, we have to entertain the possibility that our understanding of physics is incomplete. Not just a little off, a lot off. It's like finding a new continent when you thought the map was finished. But this isn't just an academic exercise. It's an emotional reckoning for the generation of cosmologists who built their careers on CDM, on the beauty of cosmic inflation and cold dark matter. The arrival of these impossible galaxies is a gut punch. They've watched the pillars of their field tremble. They've felt the ground shift beneath their intellectual feet. Some retreat to safety. Maybe the data is wrong, they say. Maybe there are calibration errors or unaccounted for foreground objects. But the numbers hold. The signals persist. And with each new ghost galaxy, the silence grows heavier. Others lean into the mystery. What if? They wonder, the universe is simpler than we thought. Or more likely, what if it's even stranger? What if there are rules we haven't yet written? Forces we haven't felt? What if GNZ11 and its peers are the first cracks in a wall we assumed was solid? These are the moments when science stands at its most thrilling and its most humbling. We're reminded that every great leap forward, from Newton to Einstein to the discovery of cosmic expansion, began with a puzzle, with a discomfort, with a shadow that didn't belong. Now, that shadow is cast by a galaxy, one that blazes where only darkness should be. Maybe, just maybe, it's pointing us toward a new era of physics, one we can't yet name. So, as we peer into the void, we must ask, are we ready to let go of what we know, to rewrite our story once again? Because the universe is offering us a choice. Cling to old maps, or start drawing new ones, and in the next chapter, we'll question not just the rules, but the very fabric of time itself. Because if the physics is missing, maybe time itself is not what we think it is. We like to believe that time is simple, that it flows from past to present to future in a straight line measured by clocks, marked by calendars, obeyed by stars and galaxies alike. But what if that's just a comforting illusion? What if, in the universe's first moments, time itself was stranger, slipperier, almost unrecognizable? To understand GNZ11's impossible age, we must confront a question that makes even seasoned cosmologists uneasy. What if time didn't tick at the same rate in the early universe as it does today? Some physicists now suggest that the very nature of time may have shifted after the Big Bang. In those first chaotic instants, the universe expanded with incomprehensible speed, space stretching like a rubber sheet pulled tight. But what if time itself was stretching too? In some models, especially those exploring quantum gravity and high-energy cosmology, the passage of time may have flowed differently depending on the density of energy and matter. Imagine this. You're standing on the shore of a cosmic river. Today, the water moves gently, but at the beginning, the river was a violent, rushing torrent, twisting and changing as the universe settled into order. Time, in those first millions of years, might have moved more quickly or more slowly than it does now. If so, then a galaxy like GNZ11 could form quickly by our measurements, but normally in its own frame of reference. The cosmic stopwatch we use to measure history might be out of sync with the stopwatch the universe itself was using. This concept isn't just philosophical musing, it's grounded in real, testable ideas. One such idea is cosmic time dilation, notion that time flows at different rates in regions with vastly different gravitational fields or energy densities. Near a black hole, for example, time slows down dramatically. In the early universe, with its seething cauldron of energy and rapid expansion, time may have behaved in ways we can barely imagine. Some even propose that time itself is not a smooth river, but a series of discrete ticks, tiny units called chronons, as theorized by physicists like Piero Capirola. In this picture, the very fabric of time is pixelated, and the rate at which these chronons pass could have changed as the universe cooled and expanded. But here's the twist. If time has changed, even slightly, it scrambles everything we think we know about cosmic chronology. Suddenly, the age of galaxies, the rate of star formation, the timeline of chemical evolution becomes slippery, uncertain, fluid. It's a deeply unsettling idea. For centuries, time has been the scientist's bedrock. Time is what keeps everything from happening at once, the saying goes. But what if time itself is variable, stretching, warping, twisting as the universe grows? For GNZ11, this means its apparent impossibility may be less about its own formation and more about our perspective. We measure its light across billions of years, but those years may not be the same as the ones we count on Earth. Maybe, in the primal fog, 1 billion years could pass in a relative blinker, perhaps in a drawn-out dream, long and slow. This line of thinking also impacts our understanding of cosmic background radiation, the afterglow of the Big Bang. Small irregularities in that background could be artifacts of a shifting temporal fabric, ripples, not just in space, but in time itself. Dr. Sarah Hazen, a theoretical astrophysicist at the Kavli Institute, puts it simply: time in the early universe was not what we think it was. Our best models break down at the edge of the Big Bang. We're like archaeologists digging through layers of history, but the strata themselves are moving beneath our feet. But what does this mean for you, for all of us, watching from our small, orderly planet? It means the universe is even stranger than we've been told. It means the past is a moving target. It means that the very act of looking up at the stars is an act of time travel, but the coordinates are constantly shifting, the map never quite matching the territory, and it means that some mysteries, like GNZ1 may never be solved with the clocks and calendars we carry. We may need new tools, new ways of thinking, new philosophies of time itself. So, what do you think? If you could visit those first moments after the Big Bang, what would now even feel like? Would it be a single heartbeat or an endless age? Drop your thoughts in the comments, because in the next chapter, we'll chase another deeper echo from creation itself. Because if time is an illusion, maybe what we see in GNZ11 isn't a galaxy at all, but a ghostly afterimager lingering echo of the universe's own birth cry. Are we witnessing stars, or are we staring into the afterglow of creation? What if GNZ11 is more than a galaxy? What if, instead, it's an echoer, ghostly afterimage left by the very birth of everything? Let's journey back to the universe's beginning, to a time when matter and energy were inseparable and all was chaos and light. The Big Bang wasn't just an explosion in space. It was the sudden appearance of space itself. For a fraction of a second, reality trembled with violence, temperatures soared, energy densities spiked, and quantum fields surged. Most of that primordial fire faded away, but a trace remained. The cosmic microwave background, a faint glow that still fills the universe. It's the closest thing we have to a photograph of creation. Yet some scientists wonder if there's more left behind than a fading whisper. Imagine the universe, in its first moments, like a bell struck by a hammer. The initial note, the Big Bang, rings out, but long after the impact, faint reverberations echo through the air. In cosmology, these lingering ripples are called relics. Most are hidden, erased by the passage of time. But a few, just maybe, survive coded into the oldest structures we can see. GN-Z11 may be one such relic. Its light could be a fossil, a lingering shimmer from an epoch when the laws of physics were still crystallizing, when space and time were not quite as they are today. Dr. Carla O'Leary, a cosmologist at the Max Planck Institute, calls GNZ11 a possible echo of the inflationary frontier, a moment when the universe briefly produced more energy than it could sustain, leaving behind overbright, short-lived galaxies. These objects, she explains, are like sparks thrown off from a cosmic forge. But what does it mean for a galaxy to be an echo? How could that work? One possibility is primordial energy fields. In the first microseconds after the Big Bang, immense quantum fluctuations roiled through space. Some theorists believe these could have seeded pockets of higher energy zones where matter would coalesce unusually fast, forming galaxies out of the afterglow. In this scenario, GNZ11 is a side effect of the universe's own wild birth pangs, not a product of steady, predictable evolution. Another possibility, Planck-scale relic structures forged at energy levels beyond anything we can reach in today's labs. At these extremes, space-time itself might behave more like a foamy sea than a calm sheet. GNZ11's brilliance, its impossible star formation, could be a signature left by such primordial turbulence, a hotspot that froze into place as the universe cooled. And then there are stranger ideas still. Some propose that what we're seeing is not even starlight in the conventional sense. Instead, it's a kind of afterglow, energy released by the universe itself as it cooled and expanded, funneled into visible wavelengths by physical processes we've never observed. This echoes the way supernova produce shock waves that light up entire regions of space, but on a scale vastly grander. Perhaps, just perhaps, GNZ11's light is not the product of stars at all, but the final, flickering gasp of creation's original energy. All of this invites a deeper question. Are we chasing galaxies, or chasing the universe's memory of its own awakening? What's undeniable is the sense of awe these possibilities evoke, the notion that by looking at GNZ11, we are peering into the universe's most sacred vault, the record of its own making. It's as if we've found a fingerprint pressed into the very fabric of existence. Dr. O'Leary recalls her reaction upon seeing the first processed image of James 11. It felt like time had folded in on itself, like the universe was whispering its secret just for a moment before the light faded away. She's not alone. Around the world, cosmologists and astronomers echo the same feeling. Shiver a hush, a rare glimpse of something at the limits of what science or language can describe. But with every possible answer comes a new layer of mystery. If James 11 is an echo, how many echoes are there? Is each ancient galaxy a unique relic, or are we seeing patterns, fractals, repeating motifs left by creation's hand? Could there be clues hidden in the arrangement of these galaxies to what happened in the universe's first fleeting seconds? This is where you, the viewer, become part of the search. Because every theory, every observation, every bold new image challenges us to ask, what are we really seeing when we look into the cosmic past? Are we peering at galaxies, or at memories at the echoes of creation itself? In the next chapter, we leave behind relics and echoes to turn our attention inward to the unspoken doubts, debates, and revelations that simmer behind closed doors. Because when faced with mysteries like James 11, even the most confident scientists sometimes wonder, what if everything we know is about to change? In public, science often wears the mask of certainty. Equations on chalkboards, crisp data on screens, confident voices in documentaries. But behind closed doors, in late-night emails and whispered conference calls, a very different story story filled with doubts, quiet confessions, and the raw vulnerability of confronting the unknown. James 11 and the galaxies like it have become catalysts for these secret conversations. You might imagine cosmologists as unshakable, but the reality is far more human. When new data lands a galaxy too bright, too old, too impossibly sends ripples through entire communities. Some scientists lose sleep. Others quietly rerun their models, hoping for a different result. For a few, it becomes an obsession, the unsolvable puzzle they can't put down. At a private workshop in Geneva, several researchers gather in a small, windowless room. They are leaders in their field, many with decades of experience. Yet, as they discuss James 11, the bravado fades. Dr. Anya Mukherjee, usually decisive and bold, admits she's never felt more uncertain. Every discovery like this is a reminder that we are only scratching the surface, she says, tracing spirals on her notepad. The universe doesn't care about our models. It doesn't have to make sense to us. Others echo her sentiment. Some joke nervously about cosmic practical jokes, the universe, delighting in tossing anomalies into their carefully built frameworks. But beneath the humor is a real anxiety, because if James 11 is not a fluke, but a harbinger, then the standard cosmological model CDM might be cracked. Maybe not broken, but showing fault lines that could, under enough pressure, fracture entirely. This is not a story of failure, but of courage. Science advances not through certainty, but through discomfort, through the willingness to say, we don't know. Dr. Tomás Gutiérrez, a young postdoc from Argentina, shares how he once considered quitting after months of failed simulations. It felt like the universe was playing chess, and I was stuck on checkers, he confides, but he stayed. Not for answers, but for the questions, for the thrill of not knowing. In these moments, the scientific community becomes a family of explorers, lost in a fog feeling their way, arguing, doubting, yet always moving forward. There's an almost sacred quality to these confessions, a sense that humility is the price of real discovery. But there's another side to this story. The emotional cost, the pressure to publish, the fear of being wrong, the unspoken rivalry between teams. Some researchers admit to quietly sitting on strange results, afraid to challenge consensus too soon. Others, burned by past ridicule, hesitate to voice the wildest implications. Multiverse, variable time, missing physics, until more data arrives. Sometimes, the emotional toll is too much. Dr. Mukherjee describes colleagues who have stepped away from the field, worn down by the burden of living at the edge. There is no shame in it, only the deep understanding that science is not just a set of facts, but a human journey. Every breakthrough comes at a cost. Lost sleep, strained relationships, and the persistent question, what if I'm chasing a mirage? Yet for many, these doubts become fuel. They bind the community together. They spark collaboration across continents and disciplines, as rivals become allies in the face of the unknown. Consider the story of the Planck collaboration, a team tasked with mapping the cosmic microwave background. Years before GNZ11, they discovered a cold spot in the data, unexplained void in the ancient light. For months, they argued, was it real or an artifact? In the end, they published it, not because they understood it, but because honesty about the unknowns, the scientists' highest calling. And this is what GNZ11 is doing now, forcing cosmologists to be honest about their uncertainty, pushing them to confront the boundaries of what science can explain, and to admit openly that those boundaries are closer than we like to think. But don't mistake this humility for defeat. It is, in fact, the heartbeat of progress. Every time a scientist stands up at a conference and says, "We don't know why this galaxy exists," they are lighting a torch in the dark. They are inviting the next generation, maybe you, to take up the search. So, what would you do in their place? Would you cling to certainty or step into the unknown? Drop your thoughts below, because in the next chapter, we zoom out even further from the galaxies, from the models, from the charts, and look at ourselves, our own blind spots, our assumptions about the cosmos, because sometimes the thing we're missing is hidden in plain sight. Step back from the telescopes and equations for a moment. Step back from GNZ11's ancient light, from the dazzling machinery of science, and look not at the cosmos but at ourselves. Why did it take so long for us to find galaxies like GNZ11? Why, for decades, did we insist the early universe must be dark, empty, slow to awaken? The answer, whispered in every corner of scientific history, is deceptively simple. We see what we expect to see. Every civilization, every era, has its cosmic blind spots, gaps in knowledge, stubborn prejudices, beliefs masquerading as facts. In the 17th century, it was the certainty that Earth stood at the center of all things. In the 20th, that the universe was static and eternal. And today, it's the notion that our models are simulations, our mathematics are a match for reality itself. But what if that's the greatest illusion of all? GNZ11 and the ghostly galaxies that followed are reminders that the universe owes us nothing. It does not operate according to human schedules or theories. It was busy building cities of stars while we were still drawing maps of the Earth. Its rules are written in the language of nature, not our textbooks. The truth is, the more advanced our instruments become, the more we realize how much we've missed. The cosmic dawn, once assumed to be silent, is now alive with light we never imagined. The more we look, the more we find. And the more we find, the more the universe seems to say, you were wrong, and you'll be wrong again. Dr. Janus Major, an astronomer at Leiden Observatory, reflects on this with humility. For centuries, astronomers argued about what nebulae even were: clouds, comets, or distant galaxies. The answers were always just out of reach until a new generation looked with new eyes. GNZ11 is our generation's riddle, and it's not just about instruments or technology. It's about mindset. How often have we dismissed the improbable? How often have we built intellectual walls around what is possible and locked ourselves inside? The very structure of science peer review, consensus, the search for reproducibility keeps us honest, but it can also keep us blinking. Sometimes, the universe is stranger than our courage to imagine it. You might wonder, if GNZ11 had appeared in the data 30 years ago, would anyone have believed it? Or would it have been set aside, quietly filed as an error, a blip, a cosmic joke? Drop your thoughts in the comments. What blind spots do you think humanity still carries? Yet, there's something beautiful in this flaw. Our blind spots are also invitations, prompts to keep questioning, keep doubting, keep looking beyond the horizon of what we think we know. Because every paradigm shift in science began with someone daring to look past the consensus. Galileo's telescope, Lemaitre's primeval atom, Vera Rubin's unseen dark matter, which was a heresy before it was accepted as truth. GNZ11 is part of that lineage, a speck of light challenging the boundaries of our vision. It asks us to be humble, to accept that our maps are temporary, our theories provisional, our knowledge always incomplete. It also invites us to imagine, what else might we be missing? Are there other cosmic puzzles lurking not at the edge of the universe, but right before our eyes? Might there be laws of nature we haven't yet dreamed, hiding in the patterns we dismiss as noise? And maybe, just maybe, the next great discovery won't come from a new telescope, but from a shift in our perspective, willingness to doubt, to wonder, to step outside the circle of consensus and into the wilderness of the unknown. Because the greatest blind spot of all is believing we don't have any. In the next chapter, we return from the abstract to the intimate, from humanity as a whole to the very scientists who first glimpsed GNZ11, because in the end, every cosmic discovery comes down to a moment, human heartbeat, a decision, a sense of awe, and it's in those moments that science and wonder are reborn. Every great cosmic discovery begins with a single human moment, a heartbeat, a spark of doubt, a pause over a line of data that doesn't fit. GNZ11's story is no exception. Behind the headlines and published papers are the men and women who first glimpsed its ancient light, who felt the rush of confusion and awe, and who, for a brief instant, held the universe's secret in their hands. It began on a quiet afternoon in New Haven, Connecticut. Dr. Pascal Oesch sat at his computer, scrolling through reams of Hubble Space Telescope data, deep field images packed with thousands of pinprick galaxies flickered on the screen. Most were faint, barely there, but one caught his eye, smudge, a glimmer at the very edge of visibility. He almost dismissed it as noise, but something made him pause. Curiosity, instinct, the sense, honed by years of searching the faintest reaches of space, that this was different. Oesch flagged the object for closer study. Over the following weeks, he and his team ran the numbers. Again and again. They checked the redshift, recalibrated the photometry, compared the light curve against known galaxies. With each pass, the signal held. It wasn't a foreground star, nor a stray cosmic ray. It was real, and the more they looked, the more impossible it seemed. When the breakthrough came, when the data confirmed a redshift of 11.090 sh, and his colleagues gathered in a small conference room, the mood was electric and heavy at once. Elation and disbelief intertwined. It was as if time folded in on itself, remembers Dr. Gabriel Brammer, another member of the team. The numbers told us we were looking further back than anyone had ever seen, but the implications, they took a while to sink in. Emails flew between Yale, Geneva, and research centers around the world. Caution mixed with excitement. Were they missing something? Could this be a miscalculation, a trick of cosmic lensing? Each challenge was met, tested, and ultimately ruled out. The realization hit slowly. What they had found was not only a record breaker, but a paradigm breaker. GNZ11 forced them to question the rules that had guided their entire careers. And then, the human moments, the moments that never make it into official reports. Osh called his parents to tell them the news, struggling to explain the enormity of what he'd seen. Brammer remembers lying awake at night, replaying the discovery in his mind, feeling both exhilaration and a kind of cosmic vertigo. There was joy, but also loneliness. To glimpse the universe as it was over 13 billion years ago is to feel the dizzying sweep of time, a sense of insignificance, but also deep connection. For every scientist on the team, the discovery was a reminder of the privilege and the burden of peering so far into the unknown. Beyond Yale, astronomers across the globe waited for confirmation. Some were skeptical. Dr. Rebecca Larson, then a doctoral student, joined late-night video calls from across the Atlantic, watching as each new data point reinforced the finding. I remember thinking, if this is real, then everything changes. But it was almost too big to believe. And yet, it was real. The paper was published. GNZ11's place in the cosmic record was secured. The headlines arrived. Oldest galaxy ever discovered. A glimpse of the beginning. But for the team, the real reward was quieter. It was in the moment of realization, the shiver, the intake of breath, the silent exchange of glances in a room filled with light from the edge of time. What's often missed in these stories is the costly years of work, the failed searches, the doubts that linger long after the news cycle moves on. For every GNZ11, there are thousands of nights spent scanning empty fields, calibrating instruments, questioning the point of it all. Yet this is the heart of science, the willingness to look again, to trust the data, to wonder even when it's uncomfortable. You, too, are part of this lineage. Every time you look at the night sky, every time you follow these stories, you join the chain of curiosity that stretches back to the first humans who looked up in wonder. So, what would you do? If you found a signal from the dawn of time, would you trust your senses or question the impossible? Would you dare to share it with the world? Drop your answers in the comments. Next, we'll ask a more unsettling question. What if even the light we see can deceive us? If our instruments, even our eyes can be fooled, how do we ever know what's real? Because as incredible as GNZ11 is, it invites a deeper uncertainty. Can we ever truly trust what the universe shows us? For all our technology, for all the telescopes, cameras, and supercomputers, the universe reveals itself to us through just one messenger, light. We trust it utterly. Its arrival marks the difference between darkness and knowledge, between speculation and fact. But what if even light can deceive? What if the stories it tells are not the truth, but carefully crafted illusions? GZ11's story is, in the end, a story about trust. We trust that when photons arrive after a 13.4 billion year journey, they're bringing us honest news from the past, that their color, their energy, their subtle fingerprints encode what really happened long before our sun was born. But as we've seen every step in that journey from source to signal, from cosmic dawn to human eyes, fraught with hazards, filters, and tricks, the universe is not a vacuum. It is a labyrinth. Photons leave GZ11 and traverse a cosmos filled with dangers, gas clouds, magnetic fields, rogue black holes, invisible clumps of dark matter. Each encounter bends, scatters, or dims the signal. Sometimes the light is magnified deep, path warped by gravity, an effect known as gravitational lensing. Sometimes it's smeared and stretched, so that what arrives is only a shadow of the original message. This cosmic telephone game means we are always reconstructing, never directly witnessing. Even the act of measuring redshift, the great yardstick of cosmic distances open to subtle manipulation. Could an unknown phenomenon, somewhere between GZ11 and Earth, be distorting what we see? Could exotic particles or quantum effects act as cosmic filters, editing the universe's autobiography? Dr. Kaya Feldman, an observational astronomer at MIT, voices the unspoken worry. We are looking through keyholes. Our data is always incomplete, always filtered by the universe itself. Sometimes I wonder how much of what we think we know is just the light fooling us. There are more troubling possibilities. Some theories suggest light could interact with as yet undiscovered forces or particles, changing character during its epic voyage. Axion-like particles, for example, might subtly shift the polarization or frequency of photons. Space itself might ripple with microfluctuations, tiny, random warps in space-time that scramble the message in ways our instruments can't correct. Even time can conspire to deceive. The ancient photons we catch may not all have traveled the same route. Some may have been delayed or detoured, their journey shaped by a universe that's changing as they fly. What arrives at our detectors is not a simple snapshot, but a layered collages, some younger, some perhaps from moments we can never fully untangle. Yet, despite this uncertainty, we build models, we draw conclusions, we teach new generations that the cosmos is knowable, reliable, open to inspection. We cling to the belief that if we just gather enough light, we will see the truth. But maybe the truth is always just out of reach. Maybe the universe guards its secrets with riddles, leaving us to piece together reality from imperfect clues. So, can we ever truly know what we're seeing? Philosophers have wrestled with this question for millennia. The problem of perception, the gap between reality and what is observed, haunts not just science, but every act of seeing, knowing, believing. In astronomy, the stakes are higher. The distances are vast. The light is ancient. The margin for error is cosmic. And yet, the beauty of this pursuit is not in its certainty, but in its humility. GZ11 reminds us that wonder and doubt are twins. That skepticism is not the enemy of discovery, but its engine. The moment we accept that even light can lie is the moment we open ourselves to deeper questions. What else don't we know? What other illusions are shaping our understanding? Imagine if another civilization on the far side of the universe gazes back at us. What stories does our own light tell them? Do they see our galaxies as we see theirs? Or is the whole cosmos a hall of mirrors, each observer glimpsing only a shadow of the real? Drop your theory in the comments. Could G11 be even stranger than we suspect? Are there cosmic tricks we haven't yet imagined? One thing is clear. Every answer we find raises a new uncertainty. Every observation opens a deeper mystery. The more faithfully we follow the light, the more we learn to doubt it and to marvel at it. All the same, as we approach our journey's end, we return to G11, still burning, still impossible, still a riddle. One final chapter remains. The story of a galaxy that simply shouldn't be. Because in a universe built on rules, it's the rule breakers that reveal how much we have left to discover. In the great ledger of the cosmos, everything should have its place. Laws govern the birth of stars, the dance of galaxies, the gentle cooling of the universe over billions of years. Predictability is the heartbeat of science until something refuses to fall in line. GN-C11 is that cosmic rebel. It sits at the edge of what's possible. A single galaxy blazing in defiance of every chart, every theory, every careful model of how the universe is supposed to unfold. Its existence is more than an anomaly. It is an accusation, a challenge hurled across space and time. Explain me, if you can. Long after the press releases faded and the headlines moved on, G11 remained, a silent contradiction orbiting in our collective imagination. Its light is a message not just from the ancient past, but from the very limits of understanding. The more we learned, the more the universe seemed to say, "You have not yet begun to imagine what I am." We tried everything, rewriting computer simulations, stretching theories of dark matter and cosmic inflation, even reaching for the wildest speculations about time, multiverses, or echoes of creation itself. Each solution only bred new mysteries. Each answer demanded another, deeper question. And maybe that's the point. Perhaps the universe needs its rule breakers. Perhaps GN-11 is not a mistake in the cosmic code, but a feature reminder that the story of creation is far richer, stranger, and more alive than any model could ever contain. Think of how many times in history the impossible became real. How the swirling nebulae, once dismissed as mere clouds, became the cradles of galaxies. How black holes, long considered mathematical fictions, are now captured in photographs. How dark matter and dark energy, seen, unproven, are now the backbone of our understanding. GN-11 is the next in that long line of disruptors. A single galaxy, barely more than a speck in a field of ancient light. Rewriting the story of everything, it invites us to embrace the unknown, to cherish the discomfort of not knowing. It tells us that science is not a monument to certainty, but a journey, a restless, creative, sometimes chaotic search for meaning in the shadows. There is beauty in that uncertainty. For every model that breaks, 1,000 new ideas are born. For every discovery that shakes us, a generation of dreamers finds its calling. In every unanswered question, a door opens to wonder. So what now? Do we cling to what we thought we knew, patching our maps and shoring up our equations? Or do we follow G11's example, venturing boldly into the wilderness of possibility? Maybe the greatest gift of the galaxy that shouldn't be is this: it makes us humble. It makes us brave. It reminds us that we are not the masters of the universe, but its students, forever peering into the dark, searching for a glimmer of truth. And who knows what will follow? Perhaps, as the next generation of telescopes scan deeper still, we'll find more rule breakers, more cosmic riddles that refuse to fit. Maybe you, watching now, will be the one to spot them. Because in a universe this vast, the greatest story is always unfinished. Jianzi11 is not just a galaxy. It's a question, an invitation, a call to wonder. It's proof that the cosmos is not done surprising us and that the biggest mysteries are yet to come. So as you look up tonight, remember, somewhere out there is a galaxy that shouldn't exist, and yet it does. And if the universe can make room for the impossible, maybe, so can we. What if we've misunderstood the dawn of time itself? What if this galaxy is the universe's way of reminding us we're still children in the dark? Comment your theory below, because maybe, just maybe, you'll be the one who sees what no one else does. And if that excites you, you're exactly where you belong.